The article in question does not cover mast clamps or hangers. This means the specific requirements outlined within that section of the code are not applicable to these components. The query arises because the authority having jurisdiction, or AUJ, mandates that mast clamps and hangers used in electrical installations must be underwriters' laboratories, or all listed. However, a complication arises because local suppliers do not stock UL-listed mast clamps or hangers. Furthermore, the manufacturing company producing these clamps indicates that UL listing is not feasible due to the nature of their application and the absence of suitable testing methods. To understand why mast clamps and hangers typically are not UL listed, and what alternative approaches can be taken to satisfy the AHA, it is important to examine the role and function of these components. Mast clamps and hangers are used to support the service mast, the rigid metal conduit that brings electrical service from the utility lines to a building service entrance. These clamps and hangers are critical for maintaining the mechanical integrity of the service entrance, ensuring the mast can withstand environmental stresses like wind and ice. The absence of UL listing for these components does not automatically imply non-compliance. UL listing is a voluntary process where manufacturers submit their products for testing and certification to demonstrate that they meet established safety standards. The nature of mast clamps and hangers means that standardized testing procedures might not readily exist to assess their performance under all conceivable conditions. This lack of standardized testing does not mean that the components are unsafe or unsuitable for their intended use. It simply means that they have not been formally evaluated and certified by underwriters' laboratories. Alternative approaches to satisfy the AHA requirements: firstly, providing documentation from the manufacturer detailing the design specifications and materials used in the mast clamps and hangers. This documentation can demonstrate that the components are engineered to withstand the expected mechanical loads and environmental conditions. This documentation should include calculations and engineering analysis to support the claim that the clamps meet or exceed relevant performance criteria. Secondly, obtaining an engineering evaluation from a qualified professional engineer. The professional engineer can review the design, materials, and intended application of the mast clamps and hangers and provide a written report attesting to their suitability. This report can serve as independent verification of the component's safety and performance. Thirdly, presenting evidence of successful installations using the same mast clamps and hangers in similar applications. If the components have a proven track record of satisfactory performance, this can help convince the AHA that they are acceptable for use. Photographs and documentation from previous projects can be valuable in this regard. Fourthly, researching alternative products that may be UL listed and suitable for use as mast clamps and hangers. While specific mast clamps may not be UL listed, there may be similar components used in other applications that have undergone UL certification. Exploring these alternatives may provide a viable solution that meets both the technical requirements and the AHA listing requirement. Fifthly, engaging in a direct dialogue with the authority having jurisdiction to discuss the situation and explore potential solutions. The AHA may be willing to accept alternative forms of documentation or evaluation in lieu of UL listing, especially if it can be demonstrated that the components meet the underlying safety requirements. It's important to understand that the AHA primary concern is to ensure the safety and integrity of the electrical installation. By providing comprehensive information and demonstrating due diligence, it may be possible to obtain approval for the use of non-UL listed mast clamps and hangers. The code provides guidance on acceptable materials and installation practices for service masts. Section 230.28 addresses service masts used for the support of open service conductors. This section requires that the service mast have adequate mechanical strength or be suitably supported. While it does not explicitly mandate UL listing, it does emphasize the importance of ensuring the mast's structural integrity. The commentary following section 230.28 provides further clarification, noting that service masts are often subjected to significant mechanical stresses due to wind and ice loads. Therefore, it is essential to select materials and installation methods that can withstand these forces. In summary, while UL listing is often preferred, it is not always a mandatory requirement. In cases where UL listing is not available, alternative approaches can be taken to demonstrate compliance with the code and satisfy the authority having jurisdiction. The key is to provide comprehensive documentation, engineering evaluations, and evidence of successful installations to demonstrate that the mast clamps and hangers are suitable for their intended use and meet the required safety standards. The requirements for service entrance equipment are detailed in the code, specifically Article 230. It covers various aspects of the service entrance, including the service conductors, service equipment, and grounding. The service entrance is the point where electrical power enters a building from the utility grid. It consists of the service conductors, metering equipment, and main disconnect. The code specifies the requirements for the size and type of service conductors, the overcurrent protection devices, and the grounding system. The service conductors must be sized to carry the calculated load of the building, and they must be protected against overcurrent by fuses or circuit breakers. The grounding system must be properly installed to ensure that the electrical system is safely grounded, minimizing the risk of electrical shock. The main disconnect is a switch or circuit breaker that allows the entire electrical service to be disconnected from the building. This is important for safety during maintenance or emergencies. The requirements for the service entrance are designed to ensure that the electrical system is safe, reliable, and compliant with the code. Regular inspections and maintenance are essential to ensure that the service entrance remains in good condition and continues to meet the code requirements. The grounding and bonding requirements are addressed in Article 250 of the code. Grounding refers to the connection of the electrical system to the earth, while bonding refers to the connection of various metallic parts of the electrical system to create a low impedance path for fault currents. The purpose of grounding is to provide a path for fault currents to flow back to the source, allowing overcurrent protection devices to trip and energize the circuit. Bonding is intended to minimize voltage differences between metallic parts, reducing the risk of electrical shock. Article 250 specifies the requirements for grounding electrodes, grounding conductors, and bonding conductors. It also covers the requirements for grounding different types of equipment, such as electrical panels, motors, and appliances. Proper grounding and bonding are essential for electrical safety. A properly grounded and bonded system helps to protect people from electrical shock and reduces the risk of fire. The overcurrent protection requirements are covered in Article 240 of the code. Overcurrent protection devices, such as fuses and circuit breakers, are designed to protect electrical circuits from excessive current. Excessive current can be caused by overloads, short circuits, or ground faults. When an overcurrent occurs, the overcurrent protection device will trip, interrupting the flow of current and preventing damage to the electrical system. Article 240 specifies the requirements for the selection, installation, and protection of overcurrent protection devices. It also covers the requirements for the location of overcurrent protection devices and the coordination of overcurrent protection devices in different parts of the electrical system. Proper overcurrent protection is essential for electrical safety. Overcurrent protection devices help to protect electrical circuits from damage and reduce the risk of fire. The wiring methods requirements are covered in Chapter 3 of the Code. Chapter 3 specifies the requirements for the installation of various types of wiring, including conductors, cables, and raceways. It covers the requirements for the size and type of conductors, the support and protection of cables, and the installation of raceways. Chapter 3 also includes requirements for specific types of wiring methods, such as non-metallic sheath cable, metal-clad cable, and rigid metal conduit. The wiring methods requirements are designed to ensure that electrical wiring is installed in a safe and reliable manner. Proper wiring methods help to prevent electrical shock, fire, and other hazards. The equipment requirements are covered in Chapter 4 of the Code. Chapter 4 specifies the requirements for the installation of various types of electrical equipment, including panel boards, switchboards, transformers, and motors. It covers the requirements for the location, mounting, and wiring of electrical equipment. Chapter 4 also includes requirements for specific types of equipment, such as emergency power systems and fire alarm systems. The equipment requirements are designed to ensure that electrical equipment is installed in a safe and reliable manner. Proper equipment installation helps to prevent electrical shock, fire, and other hazards. Special occupancies requirements are covered in Chapter 5 of the Code. Chapter 5 specifies the requirements for electrical installations in special occupancies such as hazardous locations, healthcare facilities, and places of assembly. Special occupancies often have unique electrical requirements due to the specific hazards present in those locations. For example, hazardous locations may require explosion-proof wiring and equipment to prevent explosions, while healthcare facilities may require special grounding and bonding to protect patients from electrical shock. Chapter 5 provides additional safety measures to address the specific hazards associated with special occupancies. The special equipment requirements are covered in Chapter 6 of the Code. Chapter 6 specifies the requirements for electrical installations of special equipment, such as electric signs, swimming pools, and elevators. Special equipment often has unique electrical requirements due to its specific design and function. For example, electric signs may require special wiring and overcurrent protection, while swimming pools may require special grounding and bonding to protect swimmers from electrical shock. Chapter 6 provides additional safety measures to address the specific hazards associated with special equipment. The communication systems requirements are covered in Chapter 8 of the Code. Chapter 8 specifies the requirements for the installation of communication systems such as telephone, data, and cable television systems. Communication systems often have unique electrical requirements due to the low voltage and high frequency signals involved. Chapter 8 provides requirements for the wiring, grounding, and bonding of communications systems to ensure that they are installed in a safe and reliable manner. The tables within the code provide detailed information on conductor ampacity, conduit fill, and other technical specifications. These tables are essential for selecting the proper size and type of conductors, conduits, and other electrical components. The tables are based on extensive testing and research, and they are regularly updated to reflect the latest technological advancements. The tables must be used in conjunction with the other requirements in the code to ensure that electrical installations are safe and compliant. Firstly, examine Table 310.15b16, which provides ampacity ratings for conductors based on insulation type and temperature rating. Secondly, refer to Table 310.16, which offers allowable ampacities of insulated conductors rated up to and including 2000 volts, with not more than 3 current carrying conductors in a raceway or cable or earth, based on ambient temperature of 30 degrees Celsius. Thirdly, inspect Table 310.17, offering allowable ampacities of single insulated conductors rated up to and including 2000 volts in free air, based on ambient temperature of 30 degrees Celsius. Fourthly, note Table 310.18 with correction factors for ambient temperatures other than 30 degrees Celsius for conductors. Fifthly, check Table 310.19 providing adjustment factors for more than 3 current carrying conductors in a raceway or cable. Sixthly, be mindful of Table 310.60, which gives ampacity ratings for conductors rated 2001 to 35,000 volts. Seventhly, acknowledge Table 310.61, which offers ampacity ratings for conductors rated over 35,000 volts. Eighthly, be familiar with Table 310.104, which lists conductor application and insulation. Ninthly, take note of Table 310.104c, which is comprised of conductor properties. Tenthly, see Chapter 9, Table 1, which contains percent of cross-section of conduit and tubing for conductors. The AHA plays a crucial role in enforcing the electrical code. The AHA is typically a local government agency or a qualified electrical inspector. The AHA is responsible for reviewing electrical plans, inspecting electrical installations, and issuing permits. The AHA has the authority to interpret the code and to make decisions on specific electrical installations. It is important to work closely with the AHA to ensure that electrical installations are safe and compliant. The AHA can provide valuable guidance and assistance in navigating the complex requirements of the electrical code.